we propose Text2Scene, text-driven indoor scene stylization with part-aware details. Our method creates realistic and part-aware textures for various categories of 3D objects, which can constitute high-quality virtual scenes. Also, our method is scalable that can create detailed and realistic textures for various indoor scenes. Further, diverse results can be obtained from the same 3D scene and controlled by input conditions. Our approach is divided into two main parts: understanding the 3D object and the stylization process based on that. Understanding 3D object deduces the texture parts that exhibit different materials or textures in the real world without any training labels. Basically, we create a color composition that visually match the given the object label, such as bed, in the text image embedding of clip. The subsequent scene stylization utilizes the discovered parts to first achieve coarse stylization in a tractable manner. After that, fine stylization further generates high-quality texture with clear boundaries. Text2Scene effectively addresses two challenges for 3D scene stylization. Previous stylization networks often process the entire scene or an object, which fails to capture distinctive part boundaries. This is because large-scale databases are trained with the whole images and do not faithfully represent texture boundaries. In our work, we combine the implicit semantic information of clip latent space with low-level geometric segmentation to extract part information for various categories of objects, and greatly enhance the realism of the resulting rendering. Second, stylization networks generating detailed texture consider only a single object and cannot be easily scaled to the entire scene. Our coarse-to-fine strategy keeps the problem tractable yet generates high-quality texture with clean part boundaries. Our goal is to create realistic and part-aware textures for entire scene of desired style. The input 3D scene is a mesh, composed of room structure, such as walls or floors, and objects. Additionally, we assume that individual objects in the scene have their class labels, and optionally have additional text descriptions. From these, we can generate a specification of style for objects. The desired scene style is defined with a target image IT and the text description of the scene TS. The scene style maintains overall consistency when stylizing a set of objects. Text2Scene framework is composed of several stages to achieve the goal. After structure stylization, we discover parts of objects to perform base color assignment and finish detailed stylization. The first stage of structure stylization uses texture retrieval. Given a texture set from an existing material library, we randomly sample texture on the structure components and render them. The histogram loss compares the rendered images against the input style image using the histogram loss with the distribution of color histogram. The clip similarity loss uses the text prompt, a structure of a room, to provide the context of the texture combination. Basically, we minimize the distance between the text prompt and the rendered image in the joint text image embedding space of clip. Then we select the texture combination that achieves the lowest score on the combined loss. Next, each object is pre-processed with part discovery. Part discovery aims to find parts to assign the same material or texture and ultimately create a visually plausible combination of the object. We first create an oversegmentation of an object based on geometric feature lines. We assign a color per segment such that the rendered image aligns with the class label, such as bed, in the clip embedding space. With the power of a large-scale pre-trained model, the resulting color combination provides a clue which segments need to be assigned to the same color. The pairs of neighboring segments are merged if the distance between assigned colors is within a threshold. We repeat the process to discover visually coherent parts without any training with segmentation labels. After the objects are decomposed into parts, we assign solid color per part, namely as the base color. The base color assignment handles a low-dimensional optimization space with a coarse set of discrete parts but still observes the holistic distribution of the entire scene. We optimize the base color using the combination of the histogram loss and the clip loss. The histogram loss again compares the color similarity to the input target image. The clip loss considers both individual objects and the global scene and compares the renderings against the text prompts. We render individual objects from various angles and compare them with the class label text. The embedding for the scene is also compared against the text that represents the type of scene, for example, a living room. Finally, the detailed stylization stage further optimizes the textures for individual objects to generate fine details. Detailed stylization generates the local texture values added to the base color for individual objects. The local texture values are defined with a local neural style field, as a short LNSF, for each object. LNSF is a neural network that takes the positional encoding of the XYZ coordinate, coefficients of the eigenfunctions for the intrinsic geometry, and part segment ID as input. LNSF is trained with clip loss where text prompt augments the object description with appearance style, such as minimal style. Therefore we can weakly bind the styles of individual objects in the scene while optimizing separately. We show the stylization results of diverse objects. It generates distinctive textures for different parts, for example, lamp shades, cushions on the sofa, handles of frying pans, of plant pots. The part-aware texture and strong semantic embedding enhance the realism for various categories of 3D objects. Here we provide a side-by-side comparison of our method stylizing the input mesh on the left. Text2 mesh does not use part information and their stylization deteriorates for man-made objects with clear structure. If we skip the base color assignment and directly generate the detailed texture field in a single step, the results do not fully exploit the part label contexts. On the other hand, our stylization preserves the inherent structural relationship and generates plausible texture. Now we demonstrate the stylization results of the entire scene. For a scene with the same geometry, we can define the desired stylization with a target image or a text description. Here we demonstrate samples of stylization results with different combinations of color palettes and style text. In conclusion, we introduce Text2Scene, a novel framework to generate a texture for 3D scenes. Our method utilizes the found part information and generates a globally harmonious 3D style that clearly classifies part segments. With the notion of the base color per segment, we can tractably observe the holistic distribution of the entire scene. Also, our framework easily produces stylized results by picking a target image and a simple text description. Thank you for listening.